Welcome to this session of the Severo Ochoa Thickness Seminar Series. Today we have Pooyan Dadvand. So I think that, the vast majority of people at Thickness know Pooyan, but just in case I will introduce him. He's a civil engineer by the University of Isfahan Technology, and then he moved to Spain to join Thickness in 2006? 2001. So in 2001, he did the PhD at Thickness, and he was one of the founders of the Kratos Multiphysics framework. And then in 2018, I think he moved to the industry to join the Altair company to work on manufacturing processes and these sort of things. And well, today he will present us the latest development of this regard, which is inherent strain solution for 3D printing simulation. So Pooyan, the floor is yours, and thank you for being here.
Thank you, Ruben. Okay, so let's start. In fact, here is quite difficult for me to talk about 3D printing here, having Michele sitting there. He's the guru in this, and in fact, he helped us a lot in this line of work. I will first present a little bit what is the 3D printing in itself, what are the challenges there, and I will talk about the solutions that are available for 3D printing. Then I will continue to what we did as a solver, then as a product, and then a little bit of bigger image that what it is there. So talking about 3D printing or additive manufacturing, and talking about the additive manufacturing in general, there are many ways of doing it. From, I don't know, what you know as a wire deposition or metal deposition. I'm talking usually about the metal part. So there are ways that you do by powder, by wire, by sheet, many ways of doing additive manufacturing. What is quite interesting is that you can see that there are many products around here, but when it's arrived to the laser beam powder bed fusion, you can see a lot of them. Basically, because this is one of the major markets that you have in additive manufacturing. For this reason, what we did is that we started exactly from that place also, having the market and try to target that market also from the Altair side. But we are going into the more other areas, for instance, for the binder sinter, for instance, that we have also a solver for that part, but I'm not going to enter on that side in this talk. So what is the powder bed fusion of PDA? In fact, you may also know this as a trademark, which is the SLM or selective laser melting. It's a simple, in very simple description, I can tell you that it's having a bed of powder. You start melting the part of the powder by a laser, just the part that are inside the geometry that you want to print. When you finish one layer, it goes down, and there is a recoater come. That is very important, this recoater movement, and puts another layer of the powder. If you want to see it, and then you repeat this for how many layers that you want to do until you finish the entire 3D printing. In fact, if you see, there are many peculiarities in this process. First of all is that the recoater is very, oops, I touched it. The recoater has a very slow, let's say, movement. So it's a lot of time for the cooling time, which comes quite important when you want, and it's a lot of, increases a lot the time of the, let's say, 3D printing itself. There are many, let's say, there are many characteristics that they are involved in the quality or in the final result of the 3D printing. One is the laser power, the laser velocity. These are basically is for control how energy you are adding to the system. Then you have the layer thickness. What is very important is that a typical layer thickness is about 20 micron, 30 micron. So it's very, very, very thin. And this is a serious problem you will see afterward. The laser diameter is very small also. This is also makes it very difficult to make it a very high fidelity problem. And finally, Just to understand that if you are doing a cube of 1 centimeter by 1 centimeter by 1 centimeter, the path length is about 3 kilometers. And now considering that the velocity is 1 meter per second, so you can understand that how many delta time you need if you want to really calculate only 1 centimeter cube. Saying that, you may say, okay, but why it's interesting? In fact, this is not a cheap way of manufacturing. It's not comparable at all, for instance, with casting or with molding or other ways that we can, or even machine. But it has its own interest. First, for fast prototyping, because you want to test something, you just prototype it, usually even sometimes to prototype a mold and then create a real piece, for instance. Another thing is to create very high optimized shape to reduce weight. This is important for aeronautics. For instance, here they are claiming that they are doing 40% lighter. This is a brake for the, how you call it, Bugatti Chiron car. So this is very, very expensive car. They can do what they want. So the cost is not important there. So the effect is important. Another thing is that this is something that can change the balance in a way, is that there are people that are claiming from the large manufacturer that they are saying that they are reducing the number of pieces. And this is not only makes the pieces more robust, because if you have a, I don't know, considering a connection which has 3 or 4 or 5 pieces and you have only one, and then the chain of the production also reduces to 1. So you have much less people to contact with. So in a way, it is more efficient also. But considering all of this, I don't think that it can yet compete as an economical way with the other ways of doing manufacturing, but it has its own niche of use. Okay, so in theory, you can produce any shape that you want with this technology, which is quite interesting. In fact, there are use cases that we found them very unique. These guys, for instance, they are creating radiators, heat exchangers for Formula 1 cars. So for them, what is very important is the efficiency and the smallness. So it was a block like this, 2 kilos, and it can refrigerate a Formula 1 car directly. They were saying that their ratio of the volume to surface is about 4,000. It's a very difficult thing to manufacturing if you want to do a professional one. You can use a lot of lattices structure just to reduce the weight, as this, and you can create very, let's say, organic shapes that they come usually from optimization. But printing is not fast. Michele is here, he knows. So it's, for instance, this part was printed in 6 hours. So the simulation times are really long, and the delta time is very small. Keep that in mind. So what are the important factors or parameters for doing SLM? Basically, if you want to create a correct piece without any defect, you should check your scanning strategy, which is important. It depends also to the orientation a lot. The entire deformation of the piece can change with the orientation of the piece, and correct use of supports. So supports has a very important role in creating or manufacturing. So in theory, you can create any shape, but in practice, still you have some limitation and you have some practical issues. The scanning strategies, there are many, like sequential, one way, but usually nowadays the one that is used is this one. So they put one direction in one layer and then they rotate, maybe 67, which is the standard one, or 46, I think. Then they rotate and do another one, they rotate another one. Why? If you go to the literature, and here, Michele is again here, we have here, you can see that this is the same geometry that they were printing it in a different ways. So it's like different directions and different patterns. And these are the normalized the deformation of those prints. So you can see that this is normalized to 1, and this was the longitudinal one. If you printed everything in traversal, the direction, then you get almost half of the deformation. But the good point is that if you get it, any of those in the pattern of the, let's say, rotating each layer, you can get about 80% of the deformation, but then is not ortho, it's completely, let's say, or at least isotropic in the plane. This is the reason that the people goes usually for recycling one. Then you have support. Designing a good support has its own, you need your own experience, but there are 3 types or 3 roles for the support. They are not maybe type, but they are more roles. So they are the ones that we use for supporting, because we don't want anything to move, at least a lot. Sometimes we want to anchor it, so this support should be very small, very thin, because we don't want to lose material on that side. But these ones should be quite strong, because you want to anchor it. Basically, because if not, usually the deformations of if you have something plain, it wants to go up. And this going up, if it goes a lot, it will hit the ricotta, and if it hits the ricotta, the printing goes wrong. So one of the important things is that keep it in a way that don't hit the ricotta. So you put support as anchor. There are also some thermal problems that you may get overheated some part, and you may use, for instance, the support just to connect, because support is directly connected to the base, so it can take out more heat from your system. What is the problem? Is that the supports, you should then take them out, and this is a manual thing. So you should try to put as less as possible in one way, and on the other way, you should be fine with the deformation, with the shape that you want to get, with correct anchoring, because if it's not correct anchored, it will go up. Okay, so basically, when you have a shape, you should start oriented, find a good orientation for it, then you should create some supports for it. And finally, there are some geometrical things just to slice it and pass it to the machine, okay? What are the difficulties of this process or what are the challenges? First, in my opinion, at least when I arrived to this area, with the untrained eyes, for me was very difficult to understand why it's deforming like this. It's not intuitive at all, at least for a civil engineer, just call it. For instance, you can see this is a real piece. In fact, I can even show you. And here we have a very important deformation. But the deformation is here, it's not there, for instance. Why not on top? Why it's exactly on that middle top? And this is another problem, is that the optimum orientation is not easy to guess. So at the priori, you cannot see which one would be better. It's not very easy. In fact, sometimes for me, it's still complex to decide which side would be better. Then creating and optimizing the supports is another history, so we should also go in that direction, have something for it. And finally, residual stresses that should be controlled. So they are cracks, they may result in the cracks, and there are many reasons of this. I put some reference if you want to then check the different reasons of the residual stresses, etc. Okay, so in fact, what the industrial need is, first of all, calculating the deformations. That distortions, usually what they do is that they put it another way around just to make compensation. So after deformation, you get the correct model. How to orient, they need guidance to try to orient the part, then try to optimize the support, which is quite interesting, and how to create them fast, and finding some scanning strategy, but this is or other machine parameters in general. Okay, so let's talk about the numerical solution, because I think that this is one of the important topics here, at this here in Simne. In fact, I was telling you that these operations are very, very long, and the delta time is very, very, very small. So a typical piece may have, I don't know, 10K, 10,000 layers. The laser beam diameter 100 micrometer, and then what you have 1 meter per second the velocity. If you do your calculation, if you want to have the correct calculation, let's say, getting the exact effect of the heat and the gradient of the temperature, which is more important than the heat itself, for calculating, for instance, the material properties, you need an element to be order of 10 micrometer. And delta T, it's about -6. Doing a simple calculation for a piece, a big one like the one of the Chiron, you can see that you will have about 1 to 10 elements and 1 to 10 time steps. Basically, no a day is possible. I'm not aware of somebody that can do a real big model without anything, just directly using a thermomechanical one. But I know somebody that does this in a more clever way. So how do people do this? They try to use multi-scale, they try to use adaptive meshing, so they refine the mesh exactly in the layer that they are activating, then they redefining it, performing even adaptive time, because you know that recoating time is very long, but you can pass it very fast, and then you are passing the laser, and the time should be very small. So there are many things that you can do to accelerate this extrusion. This is a very important, let's say, research topic. I'm personally also interested on it, but as a, let's say, company guy, still we don't have so much resource, or at least our clients, they don't have so much resource to doing it nowadays in a real day-by-day life. Then there is an intermediate solution that the people were doing it. In fact, that was the previous solver that we had in Alter, was based on this technology also. Doesn't survive. And the idea is to go hatch by hatch or layer by layer, use a thermomechanical solver as it is, with elasticity and everything, doing transient solution, and try to get the result from that. To my experience, this may be discussable, and they are not very accurate. In fact, in my opinion, they are not accurate at all. They are very time consuming for me, for something that is not because they are not well balanced, in my opinion. Using elastoplastic, very sophisticated procedure, just for the temperature that you are getting it layer by layer, it doesn't make a lot of sense, in my opinion. But there are many solvers in the market that are using this technology. And they are very complex to tune, because finally you don't have the material properties. They give you this powder, but you don't know that what is the exact evolution of the material properties over the temperature, with the temperature, because here it's important from ambient temperature to 2000 degrees. So it should have a good table of the properties just to replicate this kind of thing. There are other parameters that you cannot tune it very easily. For instance, the powder observation, the powder, let's say, density, the powder porosity. There are many things that, in fact, here we have Carlos. Sometimes you ask him, but it's not very trivial to be tuned. And then, putting everything together, we have another solution, which is not accurate at all. Call it inherent strain. This guy is to have an estimation. But the good point is that if these guys, they need a very large resource and take a lot of hours, this guy is not accurate. It takes hours, sometimes days, but it's not accurate. So if it's not accurate, so let's do something at least in minutes. And this is the main idea. So one of the main idea here is that understand what you can do with this solver, because you cannot predict many things with that. For instance, with inherent strain, you cannot do material calibration. It doesn't have even temperature inside, so you cannot do, for example, microstructure because you don't calculate correctly the temperature gradient, which is the most important thing to calculate the microstructures. Residual stresses, in my opinion, they are not accurate. Okay, they give you some idea that where it goes, for instance, behind the yield stress, which is the most important result usually people want. Because they want to see that if during the printing it will break, because after the printing they put it in an oven and they usually reset the internal stresses. But before that, they want to see that if in the printing, for instance, if you are passing that and it will break some parts, and that part, you may give some good estimation. But for compensation and spring back, it can work quite well if you calibrate it well. And finally, we have another one there. We call it macrothermal. That is not in the product, but we use it internally. This is something that we use it just to understand that how the evolution of the temperature is going inside because if the temperature evolution is almost constant, what we can say is that the inherent strain calibration is quite good. If the temperature is going down or going up a lot, then these deformations are not very correct. Okay. So what is the inherent strain methodology? In fact, it's quite simple. It comes just considering about what are the source of the deformations that we have inside the PBF. First, we have elastic deformation and plastic deformation, the mechanical one. So this is an elastoplastic solution. Finally, you should use. We have thermal deformation to do the shrinkage. We have the phase change deformation because when you melt and then you solidify, it has a big shrinkage to the solidification. And we have a discontinuity by layer. So in each layer that you put over the other one, there is a discontinuity. They are not continuous when you deposit. And this is something that is important to consider. And your total strain is a component, is all of them together. Saying that, the people knew that, or the people have been using inherent strain in welding many years ago, in 90s. And the idea was that you take your normal strain and you say your strain is a function of your mechanical strain and the strain that is induced by the shrinkage. And welding, they have formulations how to calculate this induced, or they call it inherent strain. And that inherent strain, they put it inside, let's say, your equation of the state of your solid equation. Then they do usually linear elastic or sometimes elastoplastic. In fact, in welding, they do elastoplastic solution, and with that they calculate a deformation, which is a good estimation of the total deformation. What's happening? They are not using temperature here, so it's not thermal at all. The trick is that they are assuming that this was hot like here, and the entire shrinkage applied directly to they calculate the shrinkage that they have basically until they arrive to the ambient temperature, and then they apply it in a way to that. This is basically the main idea. So having that, the people say, okay, next step, let's putting it for the additive manufacturing. And in fact, there were people who started to thinking and putting it in a very, I may call it first step way or rudimental way. They were using mainstream solvers, so they try to mimic that in the inherent strain with some type of temperature changes in the material and adding it that induce that strain by adding different initial temperature and putting everything to the ambient temperature. So it was trying to refigure itself. When I saw this paper, I remember that I read it, and then I said, how they tuned it? And then I read it again. It wasn't very clear. In fact, in my opinion, it was like they were getting a very strange way of calculating what is the inherent strain. It wasn't so clear, I believe, even for them on that time, because then they wrote another paper telling that what would be the value of the inherent strain. And on that paper that is there, as usual, they come with a very important, very interesting idea that, okay, let's calibrate it. Standard piece and doing it. So how it works. Now you can see it. Here we are saying that, okay, we have our epsilon, which is the elastic epsilon, deposition epsilon, plus the plastic one, thermal one, and the phase change. I put all of them together in one, call it epsilon inherent, and I calculate this epsilon inherent via a calibration. So you do this calibration specimen, there are several of them. This is called Payne, or there are people who call it caterpillar, depending where you use it. So the idea is that you should just print in the same way and in the same parameters of the machine that you want to print your piece, this Payne. When you have it finished, you just calculate, just take it out and calculate the curvature of this scale. With this curvature, you can calibrate your solver, saying that, okay, this is the calibration, you should active, it will find the inherent strain for you, and from that point, you can apply that inherent strain to your normal mechanical solution. Then I said that the total strain is this one that I calculated by the, how you call it, mechanical solution that we have, the normal one. Then we have the inherent strain that it arrives with the calibration, and we have the one that we call it the deposition. Why? Because when you have one layer and you put it, in fact, what's happened is that this layer gets deformed. Then you put another layer, but the other layer is in the original position, it's not in the deformed position, and it gets another deformation. So each time you have a difference between these parts. And this difference, in fact, if you see it from the numerical point of view, this is your initial value of the deformation. So the trick here is that you calculate your initial value and pass it as an initial strain to your solver, any of them. And on that side, what you are saying is that even though that this node, they are moving together, this first deformation of not activated elements, just this part. Then, again, the procedure of the calibration, which is important. So you can even calibrate the pieces when they are not isotropic in the plane. And for that one, you need to you need to do different type of the scanning and then combine them together to get an orthotropic, let's say, inherent strain that can be used then directly inside the mechanical one. So what are the advantages of this inherent strain? First of all, calibrator is very easy because it's only one piece. You put it, you calculate some curvature, and that's it. It's linear, it's fast, and can be used like effectively, for instance, for the compensation plan. But there is no free lunch. If, in fact, the residual stresses, they may depend highly to the temperature evolution. There are papers that they are claiming that they do this Payne. This Payne usually goes up, so your inherent strain is negative usually. That in some configuration that to make it even do that goes down, which is complete. So this calibration may give you a wrong result. In practice, it's very difficult to get that situation. But at least if there exists, it means that there are limitations. And sometimes it's not very easy to, let's say, to have only one strain, one inherent strain for all your pieces. Basically, depending to what is your temperature and temperature gradient on the space, not on the time, you may get different results for the inherent strain. In fact, there are people who are suggesting it. So using different inherent strains depending what is the temperature. So there are improvements to be done. And then talking as But the mechanical solver, to be honest, is not very difficult because it's finite, it's linear, it's quasi-static, so we start. Now I wanted to tell you that, okay, having the methodology, how we implement it and where we implement it. In fact, what we have is that I'm working in the manufacturing group of the Altair. So we are a group that working on the different manufacturing solutions. Everything started from the casting. That was a product here for most of you, you know, the click to cast. And then from Simile, they also implemented the first part of the injection molding. Then we improved it internally. We have solver for polymer foam, for sheet metal forming, metal extrusion, and also 3D printing, which is the one that we are talking about now. I don't know why it's not going now. It should go. Okay. From this one, there are three of them that I'm personally work on it. One is the casting as the first one. So this has casting, solidification, cooling, and cycling. A lot of different processes. This is a very mature solver right now. Then we have the molding one. This is by far was the most complicated solver that I have written in my life. So it's like, here is the very few cases that I know that the thermomechanical problem is two-way, it's not one-way. So it's not that calculate the temperature and then go for the fluid, calculating the stock. The fluid is a stock, so it's not very difficult. In fact, what is problematic is that the shear heating that we call it means that the energy that is released by the strain of the polymer gives a lot of temperature. And polymer is very temperature resistant. The diffusivity is very low. It's not a good conductor. And this makes it very, very, very tough. In fact, if you don't take into account that strong coupling, it doesn't work. So basically, it will say that you cannot feel. It's very tough solver, this one. And then all of them are, these three at least, they are the 3D printing, casting, and molding. They are based on the Kratos. Here, I don't need to talk about Kratos. Many of you are already implementing it. For the ones that you are not implementing it, you are always can join the project inside the GitHub. It's an open source one. Okay, so the solver by itself, it's very simple. In fact, we use directly the structural solver of the Kratos without any tweak on the side of the element technology. So it's a quasi-static linear. We're activating layer by layer. We can use tetrahedra or hexahedra. In fact, we can use quadratic tetrahedra and hexahedra. And you can see that we have a very sophisticated voxel measure also just to calculate in case that the solution is given by STL, it just take it and calculating it very fast. Something that I should pass it back to I should export it to the core of the Kratos. But only inherent strain, doing inherent strain is not the whole work, because first of all, you should improve it for performance, because by the way that this linear solver, this linear solution of the structure is very fast. If you have 10,000 layers, means 10,000 time steps, and this will need a lot of time. So what we do is that we try to do, if the question was that how we can activate more than one layer together. But if you activate more than one layer, then you have a serious problem, because that discontinuity that it was inherited by the layer by layer powder deposition, you should take it into account in some way. We did some study, and there are papers that claiming that they can do about 3 layer. In fact, it says that if it's go for 3 layer, the error is 11%, and if it go for 4 layers, the error is 52%. Then we took it in another way. In fact, we checked that okay, we can do quite interesting thing in the element itself, and finally we came up with our way of lumping that, as you can see here, it goes, for instance, this was for the 0.02 was the layer thickness. Here you can see that in 10 layers get the exact result. In fact, in 20 layers. In 30 layers, you are getting about 10% of the error. So that was an important push into the performance of the solver. This means that we can go 10 times faster or 30 times faster. And this is an important leap to the market. Then there are sophisticated things about robustness, because finally we were thinking, okay, as a 3D printing cannot have hanging things, or you cannot have something like this, because when you're printing this side, it's not supported at all. And our solver is implicit, so it will directly crash. What happened is that, and we said, okay, this part are not printable, until we found out that there are people printing something like this. Okay, calling them crazy, but they are. So we said, okay, how we can make our solver robust? What we did is that we try to find that boundary condition, find those points, and apply some special boundary condition to not exploit the result, but keep them in place. And in fact, we found them that sometimes the model is good even, but due to the voxel mesh, you have one hanging voxel mesh there, it arrived there, boom, it was going to that. Then another thing that we find out in a practical way that we should do deals with it is that the product guys, they didn't want it to have users to fix the piece just to have the spring back. And we say, okay, so let's implement the inertia relief as many other codes they have, and we implemented in fact. But then we realized that we cannot use it easily because it needs a direct solver. It wasn't converging at all with the iterative solver. So finally, we had to reformulate it a little bit in our way, just to making it again linear solver, let's say iterative solver compatible. It's worked quite well for our case. In fact, never failed from that time. So we're happy on that side. And then we said, okay, let's do some benchmarking. In fact, we did quite a lot of benchmarking. The bad thing is that usually what I don't like about 3D printing is that when they give you the data of the benchmark, they always say that this is confidential. I say, okay, guys, you may give us some model that they are even open. So a few of them that we have it open to just show you here, but usually you can see that you can even check for the different type of the inherent strain in orthotropic one. The deformation is quite good when the case is for inherent strain. I can tell you. If also we test, for instance, how is the different result that we got from the TET and hex element, just to see that if which technology we should go or what are the error there. And with that, now when we saw that okay, the solver is working well, we said okay, let's put it inside product. And here comes the work of our colleagues from the GUI, in fact, from Martin, you know him, many of you here. So this is the interface that is behind the solver. This product, we call it Inspired Print. It has several features to help you to, for instance, to make the supports, create the supports. It has automatic mesh generator, has tool for calibration. So there are things that you can use it out of the box. If you want, I can make a demo afterward if you have time. Then what is important is that this is the ribbon of the 3D printing. But the good point here is that first of all, it's very sequential. So you go print part, printer, orientation, blah, blah, blah. But the look and feel is very similar to what we have for mold, for instance, or what we have for cast. So it's quite easy for our engineers that they are giving support to go from one application to the other one and replicate an error or try to help the users. And also it's easier for users because they are the same people. Saying that, this we have sophisticated tools to help you on orientation. So basically, when you open the model, it will give you some maps and tell you what are the optimum orientation for which goal. For instance, we have for less support or reducing the time of the print. So putting it in an orientation that is less height, basically. Less support means that less hanging parts or less anchor. There is one plugin that we have from other company that they say that they also optimize for deformation. I don't know what they do. Their confidentiality. So these tools are designed to help you that how you orient your piece, because it's important. Then we have tools to generate support by one click, almost. So it's like you can change from this support to this and to that. They are only clicking here. As simple as this. So you just recreate them and you can parameterize them. And there are post-processing capabilities, basically, that show you that very simple, taking out the supports, for instance, just to visualize the things that they are important. The workflow is that you start with some print part, then you create a printer. Usually default value is quite good. So here's the part, you put it inside the box of the printer. Then you go for the orientation, use that mapping to orient it, some orientation. And then start to design, go to the supports, create the supports. It creates for you automatically the supports with the angles that you need or you're saying. And then you can personalize them, for instance, in this way. When you have them personalized, then you go for printing. So you have the final shape. And then, for instance, you can slice it just to visualize what is the slicing, if they are very close some part to the other, for instance, with the supports, or you can export it to some other machines. For running, you can run a calibration. So you will put the calibration, you calculate this, just cut off this part and you calculate this thickness, this curvature indicator. With that number, you give us to us and we calculate the calibration for you. When you calculate it, then you save that calibration in some place. For instance, usually it depends to the name of the material and the velocity and the parameters of the machine. You can store it and you can reuse it for your real calculation. So everything here is mainstream, let's say. And then you can post-process it in a different ways. But this is the only product. Just I want to have 2 minutes more, but give a bigger picture, because this product is in the chain of the other products, to be honest. So its value is not only calculating 3D printing. The value comes from the fact that if you have some piece here, how you can get an optimized piece. And this is the important point. You know, it's like they start, they do some space for optimization, they do some optimization. There are several tools in there that you can do that. When you have this, you may decide how you want to do. If you want to do casting, machining, or molding, maybe you decide for 3D printing, for instance. If you come here, then you have, from this model, you can have several prototype, depending to the spaces or the manufacturing conditions that you have put here. And from those ones, you may choose, say, okay, but I have several scenarios here. Which one I should use? Say, okay, let's do a part study. All of them have the requirements. All of them pass the mechanical test. All of them are feasible. So let's reduce the cost. You may reduce the cost first, trying to see that if it's go better for SLM, for instance, or Binder Sinter, for instance, you see that SLM at the beginning is higher cost than this one. But what happened if I reorient it? So I check the reorientation and I see that seems that not model 6 is better now. And finally, I can check it, for instance, with Binder Sinter, the real manufacturability, and see that first of all, this is not feasible. This is no. So I will arrive to saying that, okay, seems that SLM is working better, and I can have a design that I can send it to the guy that who should, let's say, do the final real calculation. But the good point is that all of this cycle is done in 10 hours by one people. So this is the main thing, is that not only having a solver there, but having the solver connected inside the whole ecosystem. That's something easy, which is interesting. So with that, I arrive to the next, which is only one slide. We were talking about multi-scale, high fidelity. My question is it possible to do it faster? And I think that this is a very important open discussion to have. Thank you very much.
Thanks, Pooyan, for the presentation. I think that there are no questions in the chat, but if there are questions in the room or comments.
Lo de confidentiality, tú no has contado nada, Nada,
Yeah, but some of them I can't. At least I told it.
¿Cómo se hace multilayer? ¿Qué elementos usas al final?
Multilayer I cannot tell you, but the other one, ¿el qué?
Are you using quadratic element end or linear?
Not yet. That will go. No, this is a good question. In fact, I wanted to put that in the slide. It's not in the product yet, but it will go. The quadratic element is will go. But there are still things about the peripheral that they are not going. For instance, one of the important things about the quadratic element and body fitted one in general, because here the big problem is that we are using voxel, and voxel they are not representing well the geometry. How we can improve it? Using body fitted meshes. If you want to use body fitted meshes, then you should have it or layer, which is very difficult to do it. In fact, it was failing all the time, this measure. And finally, we arrived to the point that, okay, let's cut the elements, as we know how to cut the elements, and we did the cut element. That goes, the prototype is working, but then the problem is our support, because many of the supports that are generated, they don't have any volume. So measure cannot measure. What we are doing is that right now we are connecting the voxel mesh of the support to the quadratic test that it was in the that the quadratic test that it's of the piece. A prototype is working, but still we need to finish testing it and checking it. But in my opinion, that is much more superior to this, but it wasn't ready to show it here. That was the reason.
Did you compare with Amphion or any other software?
No, unfortunately not, because Altair has a, how you call it, Amphion works sells in the Altair market, and when a solver is selling in the Altair market, they have a, let's say, agreement that we cannot use it in comparison with the solvers that we have. And for that reason, there are people that inside Altair, they use Amphion, but they cannot give us this data. We are looking for some client to give us this comparison because they can do. To my understanding, just to the unofficially means that to by stories that problems that the people are getting by Amphion and they are arriving to us. In case of inherent strain, they are not doing better than us. In fact, their predictions are very similar. So I don't think that Amphion is doing better in that case. My target, and I believe that with the tetrahedral, they will be completely off. We can push them completely out with the quadratic test. Their technology is much better. But my problem now is that, as I said in the beginning, we had a thermomechanical solver in market, and that one used to be very bad one. In fact, the results very good. They were completely off. It was so off that we had to take it out. So now the Inspire Print that used to be a thermomechanical solver, right now it only has inherent strain. So right now what we have on the table is to do the thermomechanical again. That's the new challenge. One of the body fitted, I believe that it will go in 6 months, it will go in the product. So that part I'm confident about it, that it's working. Again, the linear solver is a big issue for us. It's not working, the iterative solver. In fact, for the test, I don't know how you use the quadratic test, but for us, linear conjugate gradient doesn't work at all. And now Nord GMRES, and here I'm putting all the artillery of the algebraic multivariate. On the side of the, but on the side of the accuracy. So I really suggest that.
And still using the same inherent everywhere in this moment.
At this moment, yes, but this is we will change it. Definitely, we will go for the different inherent strain per temperature. This is
I just came in from a conference, and the good one. There is a sort of benchmark in US where they compete like Numiform, I think, Numishit or Numiform, never remember.
Okay.
But it's a benchmark for additive manufacturing where the largest labs in US generate experimental result in terms of synchrotron mainly. You can compete. You can also win $60K. The winner was at this conference. He's using inherent, but is let's say it's kind of multi-scale inherent.
Yeah, this is the paper. In fact, I read today, no? I remember them.
And the idea is to get an offline database of inherent based on the
same idea.
On the temperature, on the base temperature, and well, on the jump of the temperature. So at the end, you still need the thermal solution, at least to choose which is the inherent to be used.
Yes, in fact, they are these guys, no? I believe.
It is a Chinese guy.
Almost half of them.
At least the boss.
Yes, Tianchen or the boss is no, the boss is Alberto, but
no, this is not this guy. This is another one, but this is also a good one. But the one that was at the conference was Yao. I don't remember the full name. I can.
Okay, I lost it.
But well, just to say that.
In fact, this is in our roadmap. We want to do this. So time-dependent enhancement.
The problem is, I just anticipate, still exists a problem. That is, to generate this offline database, they do it using coupon or using high fidelity simulation. But the problem is that one of the condition, but the boundary condition of this coupon is that what you are building is on a substrate.
Exactly.
But if you build something as difficult as you are doing, something like this, where there is no substrate here because it is on the air, you don't have this kind of constraining, and so the inherent that you are using are, even if that they are better because of temperature, are still wrong because of the boundary constraining. So
we correct that already. This is now.
But this is the full story. So you can do it. You must be multi-scale.
That one we learned it in a very bad way. First release, before release, we realized that Ochoa was giving bad results for that. So it was like, in fact, bad result. It was giving right to other people that were giving bad result. And that was the reason, because the constraint changed. And with the constraint, the inherent strain doesn't say.
And what you did, also secret.
It's a part of the lumping. Yeah. That part we can do.
Okay, I think that Edu wanted to say something. Edu, you can unmute yourself.
Yeah. Hi, Pooyan. No, my question, I am curiosity. So, it is possible to use your solver or can say your tool for printing biomaterial, can say bones and all these things, or not?
Bones, no, but if it's metal, yes, because the plastic has a very different way of doing the things, and basically the bad thing about plastic is that they are not conductive, so their thermal problem is completely important. They are not
Okay,
like metal.
but are you thinking to work in this line just this kind right now is quite in the hot the topic just for printing bio stuff. So I don't know if it's just Altair or you
At the moment, we don't have any, let's say, plan for that. Basically, because usually we answer to the commercials on that, so there are not petitions on that side. I believe that because we are very new right now in the market with this new solver, in fact, and I believe that we need to be a little bit in market just to start having different opportunities and then see that if there is petition on that. But this can be used directly, for instance, if there is, let's say, titanium implant. For that one, you can use it. In fact, I believe that they are used, but not for the bones.
You can say bones, just say arteries or whatever. You can say just the implants. Can say.
Yeah.
Okay. Just in order, just to know. Just it was a curiosity. Yes, thanks, Pooyan. Gracias, Pooyan.
Thank you. Gracias.
So is there any other question? No. I have a curiosity, just a curiosity. How many people is working at the GUI and how many people do you have in the solver?
Okay. In the solver side, in all of this manufacturing, in these three manufacturing means casting, molding, and 3D printing, we are 6 at the moment, 7. And in the same way of looking at it, on the other side, I think that they are 8.
So same people in solver than in graphical usually.
Yeah.
Okay, that's just a way.
They are, in fact, they are 10, but they are giving to the all of the, if I want to count all of the other solvers that they are giving support, they are giving much more support. So they are about 3 other, let's say.
Okay.
No, but there are plenty of them. For many years, they were doubling us. In fact, right now we are 6 because recently we got Vicente and we reorganized a little bit. So if not.
Okay, so
I have a question. So, in terms of more in the shape optimization, do you know how often it is used reduced order modeling or other surrogate models for the shape optimization phase?
What do you mean about sort of modeling?
Simplified the surrogate model for the optimization to be faster. So I understand that also the optimization must be like a very time consuming part. So
in fact, yes, this is true. But for this kind of example that they are usually when they start doing optimization, in this case, it's a simple linear structure. So it's one step, not transit, nothing. So even though that the calculation and the calculation goes quite fast on that side, they are small ones. So that's the reason.
okay.
There is no plasticity, there is no non-linearity. So I haven't, usually I see it, I saw Martin doing it many times on live and it's like, gives a click, it's some seconds and it gives you.
Okay, so there is no need to accelerate the process.
No, not on that case.
okay, so I think that with this we can conclude the seminar and let's thank the speaker again. So thanks, Pooyan.